Okay, last time we tweaked our prime number program to make it more efficient when we were looking for numbers that were prime and they were not by using that break. But remember, we used this number that was prime, so we couldn't use that break shortcut we used last time. So let's see if we can make this a little bit more efficient when checking for large prime numbers. So what if we can eliminate all of the even numbers from our loop here, where we're not having to check stuff that's divisible by 2. That should reduce the processing time for this about in half. So how would we do that? Okay, first we need to create the special condition for 2. So we'll put an else if right here, and we'll just check to see if the number is equal to 2. And if it is, we know by definition that it is prime. So we'll set the is prime variable equal to true. And then we need to have the condition for all those other even numbers past 2 that are not prime because they're divisible by 2. So we'll put another else if in here and say else if the number mod 2, remember that's the remainder, so if that's equal to 0, that means it's evenly divisible by 2 and it won't be prime. So we'll go ahead and set is prime equal to false. And that'll bypass our else here that actually has the processing for the for loop. Okay, so that takes care of that special, or those two special conditions. But to make sure that we process this efficiently, we don't need to start at 2 any longer. We can actually start at 3, but be careful. Just because we don't check by 2, we don't want to check by any of the other even numbers either. So we don't necessarily want to check by 4, because if it's 4, it's also divisible by 2. So we can eliminate all the even numbers. So we can do that if we start at 3. We'll also have to change how we get there, right? So we can change that to, instead of plus plus, we want to go up by 2 each time. Okay, so we'll go 3 plus 2. The next time through, we'll check 5 is divisible by 5, and then 7, and then 9. So we're checking all the odd numbers, and that should make this a little bit faster. So with our same number, let's go ahead and go up and execute and compile and run this with our changes. And this pops up at a little bit over 58 seconds. So a pretty good time improvement over the last time. Roughly half, because we're eliminating about half the numbers, right? If we eliminate all the even numbers from the check, then that makes this just that much faster when we find that. Okay, so that does make it faster, but let's see if we can make it even faster. Before we do that, I want to check other numbers here. So I'm going to set our number equal to 99, and then I'm going to uncomment this because I want to see all the numbers that were divisible, and I'm also going to have my break commented out. I don't want it to stop. I want it to show me all the different factors. So if I execute this, it pops up with this. So I end up with 3, 9, 11, and 33. So what do you notice about these numbers is I probably didn't need to check all of these, right? Because 3 pairs up with 33. In other words, 3 times 33 is 99, which is the number we're checking, and also 9 times 11. So really, after we check the first factor, we don't really need to check the other ones, which the break will help with that. But for some other numbers, let's go back and check. Let's say we change this to 81, and let's execute this and see what the factors are. Okay, and our break would have gotten this one too with the 3 and the 27, so it should have broken it at 3. But you can imagine, what about this 9? Well, it's a factor with itself, right? 9 times 9 is 81. So really the highest number we should have to check is the square root of the number we're looking at. because anything higher than the square root, like 27, is going to have a lower factor, right? So 3 has to pair with 27 to multiply to that product. So let's put our big number back here. And let's go down and look at our loop again. And we'll go ahead and comment that out, and we'll put our break back. But if we look at our loop here, how can we ensure that we stop checking when we get to the square root? Well, okay, what's kind of the opposite of square root is multiplying, right? So in other words, the square root of this number as we go through I is going to be what? I squared. And just so we don't have to include the CMath library, I'm just going to do I times I. Okay, and so I times I, if you imagine we were back at 9, so 9 times 9 is 81. We want to make sure that's less than or equal to our number. Otherwise, we would get primes numbers. We would end up with perfect squares showing up as prime numbers. We don't want that. So that's the equal will take care of that. Okay, so with this adaptation and checking for the square root, still with our big number here, let's see, because now we should only check up to the square root of this number. So if we check that on our calculator and we take the square root of that, we're only going up, to something like 86,000 and something, as opposed to 7 billion and something. So that should be quite a difference in performance. And let's go ahead and compile and run that and see how that goes. And that comes out much more efficiently. So less than a second to go through all the factors to find out that in fact this number is prime. And we can look at more ways to maybe optimize this in the future. If you have ideas on how to create this, you can leave comments for me. And let me know if you want to look at more prime number programs. So we'll see, and we'll look at more of this in the future.